Okay, let's get started. So what I did on the course website was I uploaded a sample midterm from a previous iteration of this class that I gave, as well as solutions for it. So when's your test? Next Thursday. So so start preparing for it. So what will be on the test? Does anyone want me to answer that question?
Yes, please.
Yes. So the test will be chapter 1 of the CSE text. And so you may think, okay, what's chapter 1? Chapter 1 is everything from the start of the class until the pumping lemma for regular languages. Okay? Up to and including the pumping lemma for regular languages. And actually, the thing that we're going to get to today, the first part. And it'll be pretty evident why that'll be also on there. Because we're going to do more pumping lemma stuff and then one more thing with regular languages today. But everything about regular languages. So after this, we're going to switch over to a different set of languages. That different set of languages is not on the first test. Okay? So it's just regular languages. Okay? Do I need to say that again? Okay? Yeah. I need to repeat myself. So any questions about the test otherwise? I'll talk about logistics next week. Because I'm not exactly sure what the format's going to be yet. But any questions in general? Okay, so any questions about yesterday? Yeah.
Could you just do another example problem?
Yeah, another example problem. Would you guys like an example problem of pumping lemma again? Yes. Yeah, okay, cool. So we'll do another one. Other questions, yeah.
You mentioned about proving language non-regular. Can we prove a language is regular?
Yeah, how would I prove a language is regular? Yeah, give a DFA for it. Or use a closure under whatever those operations we have. Yeah. So if we have two regular languages, their intersection is regular because of closure under intersection. So if we want to prove a language is regular, but we don't want to make the DFA for it, or we're lazy or whatever, we just consider two regular languages, and if their intersection or union or concat or whatever is the target language, and they individually are regular, then the result must be. So that would be one way to prove that it is regular.
So the last lecture you mentioned about the language number of 0, 1 and 1, 0.
Yeah.
So they have to be same. That is a regular language, but number of zeros and number of ones is a non-regular language.
Correct.
So they seem very similar. So how we can go about that question?
So I won't ask a question like that. So it'll be easier than doing that type of like distinction between the two. In fact, the number of 0, 1 and 1, 0, that language is not always regular. It depends on the alphabet. And you can actually see that if you go to the midterm that I posted. So I asked a question on there where I had the alphabet be just 0, 1, and then the next question is the alphabet being 0, 1, 2. The first one's regular, the second one isn't. So it's actually a very difficult question to be able to draw the line between when it's regular and isn't. On the actual test, I'm going to say, prove that this is not regular. So, like, you won't have to make that judgment call. Unless I was evil. Do you want me to be evil? I could be evil if you want. Okay. Okay. To answer your question. Okay. Other questions just about what we did yesterday? Or in general, actually. Yeah.
Is the pumping lemma just used to prove something is non-regular?
Yeah. So think about what the pumping lemma says. Could I use the pumping lemma to prove a language is regular? No. Why? Yeah.
It's because a regular language will have a pumping lemma, but a pumping lemma doesn't necessarily mean you have a regular language.
So you may need to be more precise, but I think I know what you're saying. Look back at the statement itself. It says, let L be a regular language, then there exists all the constants and whatnot. So if we have a regular language, then it has these properties. But if we have a language that just has these properties, does that imply that it's regular? So like the converse of the statement? No. So in fact, you can find non-regular languages that satisfy the conditions of the pumping lemma, which is weird. So the converse is actually not true here. The contrapositive is always equivalent to the original statement. What is the contrapositive? Regular language implies conditions. That's the original statement. The contrapositive is it doesn't satisfy the conditions, therefore it can't be regular. Okay, which is what we did in the examples that we did. We had a language, we showed it didn't satisfy the conditions, therefore it couldn't have been regular, because if it was, it would have the properties, but we showed it didn't. Yeah, does that answer your question?
So that's the only purpose it has? There's nothing else?
Yeah, so that's why it's called a lemma. Anyone know what a lemma actually is? So if you become an academic, you have these theorems, corollaries, lemmas, propositions, whatnot. So a lemma is usually meant to indicate this is just a tiny result that's meant to be useful in proving other things. So like proving that the number of zeros and ones in the string, that language was not regular. We use the pumping lemma, the helper result, to get the result that we actually wanted. So it's kind of like a meta theorem of sorts. It's like a little theorem that we can use in many places. So that's why it's called a lemma. Other questions? Okay, so we wanted to do another example. So do you want an easy example or a cool example? Both. Okay, let's do both. So let's do this one. So let's call it L1. We're going to call it the language of just zeros, but the number of zeros is a perfect square. Okay? So I'm going to write this as 0 to the n squared, where n is at least 0. So if I pick n equals 0, that's the empty string. Pick n equal 1, that's 1 0. Pick n equal 2, that's 4 zeros, then 9 zeros, then 16 zeros, then 25 zeros, and so on. Okay? Let's show that this is not regular. Actually, this one's easy and cool, but the next one will be even cooler. Frozen. Okay, so let's talk about this language. If we want to show that it's not regular, what do we do? Pumping lemmas seems like the only way to go. So how would we actually go about doing this? So I have amnesia, obviously, and I forget what we did yesterday. Can someone help me figure out how to actually proceed? Yeah.
Yeah, so to prove it's not regular, you're going to prove it's not by contradiction.
Okay, so by contradiction. Okay.
Yeah, so first assume that L is regular.
Okay, so let's assume L1 is regular. And, okay, I remember proof by contradiction means we better get a contradiction at the end of the proof. Hence, proof by contradiction. Okay, so we assume it's regular. Okay, now what? Oh, okay, so there exists some constant for this language. Okay, so then exists, I'm going to shorthand this to make it so we don't have to write so much. Exists a P for L1. But remember that the P here always means pumping constant, always. Okay, I'm just shorthanding it to save on time and space. Okay, so So there's this pumping constant P. Okay, now what? Oh, okay, so pick a string. Okay, any string?
No, it's gonna be a string longer than P.
Oh, okay, so we gotta pick a string that is in the language. Okay, that's fine. And has what other property? Length at least P. Okay, so I'll let you guys pick since you guys are guiding me. Okay, let's see. Well, let's try. I don't want to waste too much space, so let's pick 0 to the P. Will that work? It has length at least P. See why I'm doing these examples? So, you guys have sad looks on your faces. So why do you have sad looks on your faces?
It has to be like power of 2.
Well, not a power of 2, a perfect square.
So then it's going to be like square root.
Well, let's see. Well, is P a perfect square? P stands for perfect square. So obviously it must be. Is it a perfect square? Don't know. So we don't know for sure. So this string might not be in the language. Okay, well, shoot. How do we fix this? Oh, P squared. Is P squared length at least P? Yeah, so for all integers at least 0, P squared is bigger than at least as big as P. Okay, and it's in the language obviously because it's a perfect square. Perfect. Okay, well, so now what do we do? Decomposition. Do I look at one decomposition into it first? How many pieces do I look at the decomposition? 3 okay, so 3 pieces. We called them, I think, X, Y, and Z or something. And let's see. So how many decompositions do I need to look at? Just one? Oh, all of them. Well, what are all the decompositions here? Is there something about this string that can help us a lot? How many different characters are there in the string? Different characters. Is there a 1 in this string? I need more emphatic answers. Are there any 1s in this string? Oh, thank you. So what do we know about the X part and the Y part?
All zeros.
They're all zeros. And well, Z is also all zeros. So cool. So wait, so what was our technique when we knew that the X and Y part were all the same character? What did we do here? I think you have it. Yeah, so we had alpha, but is alpha a fixed value? No, we had it range over a certain size, so at least 0 and other stuff. So we considered an arbitrary case, 0 to the alpha. So alpha is zeros for X, and beta zeros for Y, and Z having everything else. But notice it's P squared here and not P, because the original string had P squared of them. And then we took alpha and beta away. So wait a minute. So why do we look at all decompositions again? Just as a sanity check. Why are we looking at all decompositions?
Maybe just one of them.
Oh, wait, what if we left one of the decompositions out? We just said, let's not waste our time on that one. What could be the problem? What's sorry?
It could be rated.
It could satisfy the conditions, yeah. So one case could sneak through and be the one that always works. So, and we actually saw an example of that. See, I'm recalling things now. So Okay, so that's why we look at all decompositions. Well, now what do we do?
We actually picked one.
We picked what?
I.
Picked a value I, such that what do we want to happen? Well, a contradiction, of course, but what is the contradiction?
Have it like in the language.
What is?
Like have it in the language.
To have it not in the language, because the lemma said that it'll always stay in the language, no matter what value of I you pick. Well, what is the thing that will always stay in the language and that we want to get out of the language? No, what is the string that we want to consider? Not just y. Not just x, y, z. X, y to the I, z. So we want to, just to reiterate, we want to pick an I such that x, y to the I, z is not in the language L1, the language of perfect squares. What value of I better I not pick? The simple one. 1, yeah. Why not 1? Because,
In the language.
yeah, it's in the language. It's the original string. Okay, great. So let's not pick 1. What value of I should we pick, though? 2, it may work. Let's try doing it with 2. It will work with 2. So let's pick I equals 2. So x, y squared, z. Can anyone just tell me straight up what the number of zeros left is? Or the number of zeros in this string is?
P squared.
Yeah, p squared plus beta. Okay, great. Perfect. And what is our goal with this string? What do we want to know about that string? It's not in the language. Okay, that's what we want to prove. Could it be in the language, though? Could p squared plus beta, so this implies, could p squared plus beta be a perfect square? If we can prove it isn't, then we know that string is not in the language and we're all done. Let's see. What do we know about beta? What are some statistics we know about beta? It's at least 1. Okay, so that's fine. So we know beta is at least 1. Well, let's see. Could p squared plus beta equal p squared? No, why not? Beta would have to be 0. So we know for sure that this cannot be p squared because implies beta equals 0, which we know is a contradiction. Well, proof's done. It's not a perfect square. Class dismissed. Why is that not sufficient proof? Oh, could it be a different perfect square than just p squared? That could be a problem. Because it could be, say, the next perfect square, right? Well, wait, okay. Let's try to get some analysis of what could happen. What is the next perfect square above p squared? We know it can't go below p squared because it can't be equal to it, but it could be the next one. So what is the next one? P plus 1 squared. Okay, great. So next perfect square is p plus 1 squared. Okay, that's fine. So now put on your middle school mathematics what is this expanded? Yeah, p. Just FOIL it out. P squared plus 2p plus 1. Okay, well, we know that beta is at least 1, but maybe we want to also know, okay, it's at least 1, but it's at most a certain number. So the question then becomes, well, it's at least 1, but what is the highest value that it could have? P. Why? Oh yeah, we know that the condition xy is at most p characters. Well, is there anything in the conditions that says that x has to be non-empty? No, there's no condition like that. So the only thing along those lines is y has to be empty. So let's just consider x to be empty for a moment. Well, it could be that y takes up all p characters in length. So therefore, beta could be at most p, or it could be equal to p. So we also know then that beta is at most p characters. Now, remember, this is an arbitrary decomposition. Beta could be much smaller, or it could be equal to p. We're treating all decompositions at the same time. But we know for sure it's at most p. It can't be more. Any questions on why that's true? Okay, so that's helpful. So we know that the next perfect square has no betas at all in it. But the length of the string we have does have a beta in it. So, but the thing is, the string's length could vary because beta could vary. Well, do we know how long the string could be? The absolute longest it could be. Well, p is fixed. That can't change. Can beta change? Can beta, the length of y, change depending on the decomposition? Yes. What is the biggest it could get? P. Oh, so that must mean that from this, the length of the string that we are considering is at most p squared plus p. It could be that long, but we know it can't be any longer. Okay? Oh, wait a second, says Ryan in a startled voice. Look at these two lengths. What can you see between them? Well, that'll be true. But what about these two quantities? What can you tell me? Well, they're not equal, obviously. But can you say something stronger than they're not equal? What can you tell me about the p squared plus p, relative to the next perfect square? What can you tell me? It's always smaller. Wait a second. So let's see. Are there any other perfect squares between p squared and p plus 1 squared? Are there any in between? Oh, wait a second. So this tells us that the length of the string is strictly between two consecutive perfect squares. And it's not equal to either of them. What do we know about the length of this string now? It can't be a perfect square. Why? It's strictly between two consecutive ones, and it's not equal to either. So we know then length of that string is not a perfect square. So then it's not in the language, meaning that L1 is not regular. Doesn't that give you goosebumps? It gives me goosebumps every time I prove this. I proved this probably 20 times at this point, but I just love how slick this is. And it's not a long argument either. It's, what, a page? And it's using pretty much the same ideas we've been doing. So recap. We wanted to pick a string that's in the language and long enough, so we picked the p² one. We looked at all decompositions like before, and we picked I equals 2 because that's one that'll actually work. Based on these two quantities, the p² plus p and p² plus 2p plus 1, what is another value of I that'll work? 3. Because if we pick 3, the length of the string will be at most p² plus 2p. But then the next perfect square is p² plus 2p plus 1. So it's always still between those two values. So yeah, I equals 3 will work, but I equals 2 is certainly okay. So then we just looked at the length of the string and tried to realize, well, could it be a perfect square? We know it's not equal to this one. And then we thought, well, it could be the next one. So we tried to make an analysis of, here's the next perfect square. Could the length of the string be equal to it? And it turns out, no, it's strictly less than that number. So therefore, it's strictly in between, and it can't be equal to a perfect square. Any questions? Yeah.
So right now, you're saying that we have to test all cases. So every time we're trying to prove something or confidently prove something, we always do all the cases, right? So if we use X, Y, and Z, is there ever a time that we just use like X and Z or like Y, like not all three of them?
Good question. So it's like, are we going to always use that condition that beta is at least 1 and whatnot? You will always use the Y condition. It turns out that the condition XY is at most P characters. That turns out to not be a completely necessary condition, but the other two conditions, that Y is non-empty and then no matter what I you pick, you stay in the language, those two are always required. And I'm not, it's not just like I'm requiring you to do that. That's literally required of the actual lemma to be even able to apply it. Because if you drop one of the conditions, then the lemma actually turns out to not be true. So it's just a result of the lemma itself. But we use the xy less than or equal to p condition because it's very helpful. Other questions? I could do one that'll blow your mind, but do you want to do that one, or do you want to move on to other stuff? Do that one. Okay. Everyone's going to hate you now. Well, not now, in like however long. So let's do a very similar language. Yeah, let's do that one.
Was that the easy one?
Yeah, that's the easy one. Yeah. Well, easy. The next one's kind of along the same lines, but the only difference between them really is that the next one we're going to do, you don't pick a specific value of I, but you pick a value of I based on the decomposition itself, and it'll result from computation that we do. Because we'll just say, oh, we don't know what value of I to pick, and then we'll be able to pick it at the very end. So we don't have any choice as to what we need to pick. And it'll fall through easier. Yeah.
That had a formatting beyond
What do you mean formatting?
I mean, like proving all of that.
Yeah. Mm-hmm. Other questions? Okay, so let's move on to this language because you asked for it. It's very similar language, but now I want primes. And I want to prove that this is not regular either. And so here's something I want you to realize. If you write a program that, say you write a function that takes in an integer and determines whether it's equal to a perfect square or it does a primality check, by this reasoning, there's no DFA that can prove that your program's correct because those languages are not regular. Isn't that kind of weird? That this model computation can't prove that your program is actually correct. which is pretty interesting. But let's prove that this is not regular. So proof. Do we have time for it? I think so. So yeah. So how do we begin? Yeah, assume L2 is regular. Going back to your question earlier, pretty much all pumping lemma style proofs are going to be have the same recipe. So it's like you assume that the language is regular, then there exists a pumping constant p, and then you pick a string, and then analyze cases, and then pick the value of I at the end. It's pretty much the same strategy. Okay. Although there are other strategies that are easier, that's the one for pumping lemma. I'll show you a different strategy in a bit, if I remember. Okay, so assume L2 is regular. So then what do we assume now? Yeah. And another thing I want you to realize is that even though this is like it's kind of getting routine, like you're doing assume, exists, pick a string, I want you to think about why you're doing each of these. Why are we assuming that it's regular? Because we're doing a proof by contradiction. Why are we assuming that there exists a pumping constant? Because then there exists a DFA for this language under that assumption with some number of states, and we're letting that number of states be P. So understand why we're doing these things. Okay, but there exists a pumping constant P for L2. Now what do we do? Yeah, pick a string. And what do we require of the string itself?
For the language.
It's in the language, and it's the same two conditions every time. Length at least p. So here's one. So we're going to choose 0 to the p as the string. P stands for prime, so therefore this is the right string. What's wrong with it? We don't know if p is prime. Well, that's an issue. Shoot. What do we do? Well, could we just keep going up from p and just keep increasing by 1? And are we going to hit a prime at some point? Be careful. Are we going to hit a prime at some point? Yes. Why?
There's always a prime bigger than...
But why is that true? Why is there a prime always bigger than any integer you pick? Pick any integer, there's a prime at least that number. Why is that true? There are infinitely many primes. So this goes back to Euclid. So Euclid said, I don't think he said it exactly like this, but there are infinitely many primes. Okay. So we can't pick p as the length, obviously, because it might not be prime. Well, what if we picked a prime that's any prime at all, at least p? Is that okay? As long as we pick some prime that's length that has size at least p, is that okay? Yeah, because the length is okay, and because it's prime, we can guarantee that it exists. Because it's prime, it's in the language, by definition. So, forget this. We're going to choose we're going to choose a prime r at least p, and I'm going to leave a little space because I'm going to modify it a little bit. We're going to choose a prime that called r at least p, and the string, let's see, w equals 0 to the r. So it does have a prime number of characters and has the length requirement fine. I'm going to actually make a very slight adjustment, and we'll see why. Instead of at least p, I'm going to do it at least p plus 1. Is that still okay? Yeah, I don't want to fool you here. So, because p plus 1 is still an integer, there's still a prime at least that number. Cool. So we got the prime thing okay. Well, we could go through the decomposition, whatnot, but here's the thing. Do I care about what the string actually is, or do I care about the length itself? We only care about the length itself, right? So, yeah, that's all we care about. So we want to know, for any decomposition that we can possibly pick, whether we can pick an I such that the result is not prime. So what is a short proof if I give you a number and you determine that it's composite, so not prime? How would you prove that to me?
Just find one. Two numbers that multiply.
Two numbers that multiply to it. What else do I need to know about those two numbers? What if I just pick one in the number itself? Those two multiply to equal that number. Right, so they need to be both at least, not one, at least two. Okay? That's where the plus 1 comes in. To guarantee, no matter what we do, we'll have something at least 2 times another something at least 2, and that'll multiply to equal this r. Okay? So we're going to look at any decomposition into x, y, z according to the rules. So I'm not going to write x equals blah, y equals blah, z equals blah, because I don't care. We're only concerned about the length of the string. Well, here's the thing. What value of I should I pick? I have no idea. So one technique that you can do in these types of proofs is not pick a value of I. Just handle it in the general case. And then at the very end, you pick the value of I that works. Okay? So like for the 0 to the p, 1 to the p example that we did, we could have done that in the general case. Instead of just picking I equals 2, we could have just said, oh, I don't know what value of I to pick. I'm just going to save the work of figuring out what value of I to pick until the end. And then I pick the value of I that works, or some value that works. So let's see. We want to pick a value of I such that x, y to the I, z, the length of it is, let's see, is not prime. Okay, so that's our goal, right? We want to look at any decomposition and then pick a value of I that's good. And by good, I mean is the resulting string's length is not prime. Anyone confused about what we're doing so far? Any questions at all? Okay, well, let's see. So let's look at that length. And I'm going to rewrite it a little bit. I'm going to do things that are controversial right now, or shouldn't be controversial, but I want you to tell me whether it's controversial or not. So is the length of this string equal to the length of xz plus the length of y to the I? So is the length of the whole string the same thing as the length of the first and third piece plus the length of the middle piece? Is that okay? Yeah, because you can just think of it of breaking the string into 2 parts and then just measuring the length of each. And I didn't delete or add characters along the way, so we're okay. What about this? So is this equal to the length of xz plus I times the length of y? So remember, y to the I means y pasted with itself I times. Is that the same thing as saying I times the length of the string without the exponent? Is that okay? No, I want you to really be sure. Is this okay? Well, if I have the string 3 times, is that the length of that the same as saying 3 times the length of just one of the 3 pieces? Yeah, because it's literally just a string 3 times, and I'm just multiplying it on one of the pieces. Okay, and our goal is obviously, because these are all equal, to show that this is not prime. Okay, now we still have the conundrum of what value of I do we pick? So let's not look at this particular length, but I'm going to look at a possibly different length, and then we'll see that they're actually the same. Let's look at this. So let's look at the length of xz times the length of y plus 1. Okay? What is this number? It's not necessarily the same as the original, because there's no I in here. But let's see. What is the length of y always, at least? 1. Wait a second. What is this, at least? At least 2. So that's good. If we have something times another something, and one of the pieces is at least 2, we're all set, right? This is not prime. What about the xc part?
X's are whole, because any number times 2 is
Xc could be 1, and y could be 1, so it could be 2.
Yeah, well, yeah, 2 is the only.
But here's the thing: xz could be 1, and then the y plus 1 part, that could be the prime itself. So it could be 1 times the prime. But hold on a second. What is the length of xz at least? Well, let's go back up. What is the length of y at most? P. Oh, shoot. My bad. This should be at least p plus 2. My bad. I thought p plus 1 would work. Turns out p plus... Yeah, it should be p plus 2. Yeah, there's a little issue with the 1 and the 2 here. But the 2 I know definitely works. Let's see. What is the length of y at most? P. How many characters are left over at least? 2. Because we picked one at least p plus 2. Oh, well, y could take up to p characters, but we know that therefore there are at least 2 left over. What parts of the string have those 2 characters in them? Well, z and x. Well, I don't know where necessarily, but both of them together have the 2 characters. So we know then this part is also at least 2. So therefore, this product could not be prime. Okay? But this is not the same as the length of the string we had. Right? The length of the string we had an I in it, and this doesn't. How do I transform the length of the string that we had with the I into this length that we know is not prime? Right. So what we do is to get the result we want, we set I equal to the length of xz. And if you plug that in, we get the exact result that we want. So if we plug in I equal to the length of xz, then we get that product that we have below, which we know is not prime. But let me not fool you here. Can we do this? If we can, great. But can we actually do this? Maybe not. But think back to what the pumping lemma said. It said, for there exists a decomposition into the three pieces such that then one of the conditions had the I in there. So there's nothing that says that I had to be fixed for all decompositions, for any decomposition that we pick. As long as we pick some value of I that may depend on the decomposition itself, if we can do that, then this follows through. So in fact, we can do this. So it's not always the case that we'll have a value of I that is just a fixed number like 2 or 3 or 0. Sometimes we can make it depend on the decomposition itself. So wait a second. If we pick this value of I, what do we know about the length of the string then? What's that? Well, it's at least 2, but it's something at least 2 times something else at least 2. What do we know about that then? It's not prime. So the length of x, y to the I, z is not prime under this choice of I. Okay? So that means that the language is not regular. So there is absolutely no way I'm going to ask you something that hard on a test. But I want you to be able to appreciate the fact that you don't have to pick the same value of I every single time. In fact, if you break sometimes into this case and this case and this case, you can pick a different value of I every time. Whatever one is most convenient. You don't have to pick the same one every time. And in fact, sometimes you can't in order to get the result you want. So I just want you to be able to appreciate that. But any questions on the actual proof itself? Yeah.
What do we choose I to be?
Yeah, so we chose I to be this so that the length of the string becomes this quantity. So if you plug in the value of I that we picked into there, then you can factor the length of xz out and we get that, and we know that this is not prime. So that's one way you can go. There are other values of I that you can pick here, so this is not a unique thing, but it's just one way to go. Other questions? So remember, I'm not going to ask you anything near this hard, but I just want you to be able to appreciate how we're actually doing the steps one at a time. But any questions?
What about the first one? Are you going to ask us the first one?
Could you do n cubed? Or 2 to the n? These are hints to you, by the way. Could you do n cubed or 2 to the n? Or number of zeros is less than the number of ones, or some variation on that? Okay? Any other questions before we break? Because I know we need one. Okay, let's take a break.